Hey everyone, welcome back. In this project, we're building a neural network from scratch in C++ to classify whether a point lies inside or outside a circle. In the previous video, we implemented the activation functions, the matrix class, and set up the beginning of our neural network class, including weight initialization. In this video, we'll move on forward by adding the forward propagation logic, and we'll also implement the training process with backpropagation and gradient descent. Okay, let's bring this neural network to life and let's get started. Let's implement the forward pass, the process where we take an input, pass it through the network, and generate an output. This is how our neural network makes predictions. We define a method called forward, which takes a vector of inputs and returns a vector of outputs. Here's how it starts. Vector, double, forward, and it takes const, vector, double, reference input. Inside the forward method, the first thing we need to do is verify that the input size matches the expected number of neurons in the input layer. A mismatch could lead to incorrect computations or even runtime errors. To ensure this, we add a simple check. If input.size is not equal to layer sizes square brackets 0. And here we say throw runtime underscore error, and we pass it this message. Input size mismatch. Next, we create a vector to store the activations of the first hidden layer. And we say vector double hidden 1 inside parentheses layer sizes square brackets 1. Now we loop through each neuron in the first hidden layer to compute the weighted sum of inputs from the previous layer. And we say for int j equals 0 and j less than layer sizes square brackets 1 and j plus plus. And inside this loop we declare double sum equals and initialize it with neurons bias 1 square brackets j. Next we loop through all neurons in the previous layer, the input layer, and here we say for int I equals 0, I less than layer sizes square brackets 0 and I plus plus. And here is the weighted sum plus equals input I times weight 1 I comma j. We multiply each input by its corresponding weight. Finally, we apply the activation function to introduce nonlinearity, and we store the result in hidden 1 square brackets j equals activation colon relu, and we pass it sum. Now we do the same for the second hidden layer. First we declare a vector to store the activations of this layer like this. Vector double hidden 2 layer sizes square brackets 2, and we loop through each neuron in this layer just like we did for the previous one, and we say for int j equals 0, j less than layer sizes square brackets 2 and j plus plus. Then, just like before, we initialize the sum with the bias, accumulate the weighted inputs from the previous layer, and apply the ReLU activation. Okay, let's do it. Double sum equals bias 2 square braces j, and for int I equals 0, I less than layer sizes, square braces 1, and I plus plus. And then inside the loop, sum plus equals hidden 1, square braces I, times weights 2, parentheses I comma j. And here we apply the activation function. Hidden 2, square braces j, equals activation colon colon ReLU, and we pass it sum. And again, we repeat the same process for the output layer. However, this time we use sigmoid activation function instead of ReLU. And we start like this: vector double output layer sizes square brackets 3. Then we loop through the layer for int j equals 0, j less than layer sizes square brackets 3, j plus plus, and double sum equals bias 3 square braces j. For int I equals 0, I less than layer sizes square braces 2, I plus plus, and inside the loop we say sum plus equals hidden 2 square braces I times weights 3 I comma j. And next we apply the activation function. Output square braces j equals activation sigmoid, and we pass it sum. Finally, we return the output. Return output. And that's it for the forward pass. Now we define the training method, which handles the learning process of our neural network. It takes a set of inputs and corresponding target outputs, along with a learning rate to control weight adjustments and the number of epochs, which determines how many times the network will go through the entire dataset. Void, train, and it takes const, vector, vector, double, reference inputs, and const, vector, vector, double, reference targets, and double, learning rate, and int epochs. Before we start training, we need to ensure that each input has a corresponding target output. If the sizes don't match, it means our dataset is inconsistent, so we throw an exception to prevent issues. And here we say if inputs.size is not equal to targets.size. Then we throw an exception. Throw runtime underscore error, and we pass it this message: input and target sizes don't match. Next, we set up a loop to run through the training process multiple times. Each full pass over the entire dataset is called an epoch, and we repeat this for the specified number of epochs. So we say for int epoch equals 0 and epoch less than epochs and epoch plus plus. Now we declare a variable total error and initialize it to 0.0. Double total error equals 0.0. This will help us track the overall error across all training samples in each epoch. And next, we loop through each training sample in a dataset using k as the index. This allows us to process one example at a time, updating the network accordingly. And here we say for size underscore t, k equals 0, k less than inputs dot size, and k plus plus. Now we're going to repeat the forward pass inside the training loop. This is necessary because during training we not only need the final output, but also the intermediate pre-activation values for backpropagation. The key difference here is that we store these values to compute gradients later. So we declare a vector of doubles for the first hidden layer, which will store the activation of its neurons. Vector double hidden 1 layer sizes square brackets 1. And then we declare a vector called hidden1 pre to store the pre-activation values of the first hidden layer, which will be used in the gradient descent calculations. Vector double hidden1 pre layer sizes square brackets 1. Next, we loop through each neuron in the first hidden layer for int j equals 0, j less than layer sizes square brackets 1, and j plus plus. And just like before, we calculate the weighted sum. And here we say double sum equals bias 1 square brackets j. And for int I equals 0 and I less than layer sizes square brackets 0 and I plus plus. And inside the loop, sum plus equals inputs square brackets k square brackets I times weights 1 I comma j. And here is the pre-activation value. Hidden1 pre square brackets j equals sum. And then we say hidden1 square bracket j equals activation ReLU sum. And we repeat the same process for the next hidden layer. Vector double hidden2 layer sizes square brackets 2 and vector double hidden2 pre layer sizes square brackets 2. Then we loop through the neurons for int j equals 0 and j less than layer sizes square brackets 2 and j plus plus. Then we say double sum equals bias 2 square brackets j, and we're going to calculate the weighted sum for int I equals 0, I less than layer sizes square brackets 1 and I plus plus. And here's the weighted sum. Sum plus equals hidden1 square brackets I times weights 2 I comma j. Then we're going to have the pre-activation value. Hidden2 pre square bracket j equals sum, and then the activation value. Hidden2 square bracket j equals activation ReLU, and we pass it sum. And once again, we repeat a similar process for the output layer. Vector double output layer sizes square brackets 3 and vector double output pre layer sizes square brackets 3. Now we loop through the neurons for int j equals 0, j less than layer sizes 3 and j plus plus. Then inside the loop, double sum equals bar3 square brackets j, and we calculate the weighted sum for int I equals 0, I less than layer sizes, square brackets 2, and I plus plus. Sum plus equals hidden 2, square brackets I, weights 3, I comma j, and output pre square brackets j equals sum, and output square brackets j equals activation sigmoid, and we pass it sum. Now we calculate the error for reporting. This helps us track the network performance during training. And here's the code for nj equals 0, j less than layer sizes, square brackets 3, and j plus plus. And inside the loop we say double error is equal to targets square brackets k square brackets j minus output square bracket j. And then we square the error because the mean squared error MSE requires squaring individual errors, and we accumulate it into total error for later averaging. In fact, the error represents the difference between the predicted value and the actual value. And here we say total error plus equals error times error. Next, we're going to compute the gradients. We compute the gradients for the output layer. And we start by declaring a vector called output gradients. And we say vector double output gradients, and inside parentheses layer sizes square brackets 3. This vector will store the gradient values for each neuron in the output layer. The gradients indicate how much each neuron's activation, weights, and biases should change to minimize the overall error. Okay, let's compute the values for output gradients. For nj equals 0 and j less than layer sizes square brackets 3 and j plus plus. And inside the loop we say output gradients square bracket j equals, and inside parentheses output square bracket j minus targets square brackets k square brackets j, the difference between the predicted value and the actual value, and times activation sigmoid derivative, and we pass it output pre square brackets j. We pass it the pre-activation of that neuron. Next, we compute the gradients for the hidden 2 layer. We start by declaring a vector called hidden 2 gradients, which will store the gradients for each neuron in this layer. And here we say vector double hidden 2 gradients and layer sizes square brackets 2. To compute the gradient for each neuron in hidden 2, we first determine how much error is propagated back from the output layer. This is done by summing the contributions of the output gradients scaled by the corresponding weights. And here we say for int I equals 0, I less than layer sizes square brackets 2 and I plus plus. And inside the loop double error equals 0, and then for nj equals 0, j less than layer sizes square brackets 3 j plus plus. Now we calculate the error value. And here we say error plus equals output gradients square bracket j times weights 3 I comma j. This error value represents how much each neuron is hidden to contributes to the total error in the output layer. Since we use the ReLU activation function in this layer, we multiply the error by the derivative of ReLU to get the final gradient for each neuron. Hidden to gradients square brackets I equals error times activation ReLU derivative, and we pass it the pre-activation of the neuron hidden to pre square brackets I. Now we move on to compute the gradients for the hidden 1 layer. The purpose is the same as for the hidden 2 layer. We want to determine how much each neuron's activation, weights and biases should change in order to minimize the overall error. We start by declaring a vector called hidden 1 gradients, which will store the gradients for each neuron in the hidden 1 layer. Vector double hidden 1 gradients layer sizes square brackets 1. Then we need to compute the error for each neuron in the hidden 1 layer. For int I equals 0, I less than layer sizes square brackets 1 and I plus plus, and inside the loop double error equals 0, and for in j equals 0, j less than layer sizes square brackets 2 and j plus plus. Next we say error plus equals hidden 2 gradients square brackets j times weights to I comma j. Once we have the error, we multiply it by the derivative of the activation function applied to the pre-activation value for each neuron in hidden 1. This gives us the final gradient for hidden 1. And here we say hidden 1 gradients square brackets I equals error times activation ReLU derivative, and we pass it hidden 1 pre square brackets I. Now that we have computed the gradients for the layers, it's time to update our network. Specifically, we'll update the weights and biases using gradient descent, which helps minimize the overall error by adjusting the parameters in a direction that reduces the error. Let's start with updating the weights between the hidden 2 layer and the output layer. The weights are stored in weights 3, and here we say for int I equals 0, I less than layer sizes square brackets 2 and I plus plus, and for int j equals 0, j less than layer sizes square brackets 3 and j plus plus. And here we update the weights. Weights 3 I comma j minus equals learning rate times output gradients square brackets j times hidden 2 square brackets I. Okay, let's move on to updating the biases. Biases are important because they allow the network to shift the activation function, which makes the model more flexible and better able to fit the data. Just like the weights, biases are updated using gradient descent. The update for bias 3 is gonna be like this. For int j equals 0, j less than layer sizes square brackets 3, j plus plus, and inside the loop we say bias 3 square brackets j minus equals learning rate times output gradients square brackets j. Now let's move on to updating the weights between the hidden 1 and hidden 2 layers. The weights are stored in weights 2. Here is how it looks in code. For int I equals 0, I less than layer sizes, square brackets 1, and I plus plus. And then for int j equals 0, j less than layer sizes, square brackets 2, j plus plus. And here is the update. Weights 2, I comma j minus equals learning rate times hidden 2 gradients, square brackets j times hidden 1, square brackets I. And we update the biases for the hidden 2 layer. For int j equals 0, j less than layer sizes, square brackets 2, j plus plus. And bias 2, square brackets j minus equals learning rate times hidden 2 gradients, square brackets j. Now we update the weights between the input layer and hidden 1 following the same approach as before. For int I equals 0, I less than layer sizes, square bracket 0, I plus plus. And for int j equals 0, j less than layer sizes, square brackets 1, and j plus plus. And inside the loop, weights 1, I comma j minus equals learning rate times hidden 1 gradients, square brackets j times inputs, square brackets k, square brackets I. And we update the biases for the hidden 1 layer, and here we say for int j equals 0, j less than layer sizes, square brackets 1, j plus plus, and inside the loop, bias 1, square bracket j minus equals learning rate times hidden 1 gradients, square brackets j. To keep track of the training progress, we print the mean squared error MSE every 100 epochs. This helps us monitor how well our network learning over time. Let's do it. If epoch mat 100 is equal to 0, cout epoch MSE colon and total error divided by inputs dot size, and we add on a /n at the end. And that's it for this part. We have successfully added forward propagation and built the core of our training process using backpropagation and gradient descent. In the next video, we'll generate some training data, train our neural network, and evaluate how well it learned to classify the points. If you are enjoying the series and finding it helpful, consider subscribing and turning on notifications so you don't miss the next part. Thanks for watching, and I'll see you in the next one.